A great day. So, yesterday we looked at standing waves. So, remember, standing waves are created when we basically trap a wave between two surfaces. And as that wave bounces back and forth, the crests of the incident wave and the troughs of the reflective wave experience destructive interference, so that way it looks as if parts on that string are no longer moving. Okay, so just as a refresher, remember that standing wave is a wave in which we're basically bouncing this wave back and forth so that certain areas look as if they're not moving. And it determines the velocity of that standing wave on a string. So here, we cannot have a wave on a string unless we have a string, right? So this is going to be an example of a mechanical wave. And remember, a mechanical wave, the speed depends on the medium. So basically, what this means is different factors about the string will determine how quickly our wave is able to propagate. Okay. So, what about our string is going to determine how fast a vibration will pass on? The main thing that will determine how fast that vibration passes on will be how tightly packed are those particles, okay? So if we look at our string, what's going to determine how fast that wave will move will be the material or the thickness of that string. Okay, so how closely packed are those particles? Okay. And what the material and thickness of the strings are going to relate to is something called our linear density. So you guys may remember density as a chemistry term. In chemistry, we looked at density as mass over volume. Okay. Here, since we're looking at linear density, we're going to find linear density, which is represented by mu, that little fancy u. That's going to be equal to the mass of our string divided by the length. Okay, so how is the mass, or how are the particles of that string distributed throughout the length? We're going to look at the other factor that will determine the speed of a string in this little simulation that will determine how fast our wave moves on a string. It's going to be the force of tension. So before I get into that, just as a little reminder, here we can kind of see a standing wave start to form. You can see our wave is reflected back as it hits that surface, and it appears as if there are places in that wave that do not move. It's just kind of bouncing back and forth. Okay, so we're going to go ahead and pause that, and we're going to pulse mode. And we want to see how tension will impact the speed of that wave. Okay, so, oops, I gotta pulse it. Here's kind of the medium amount of tension as our base reference. So if we increase it to a large amount of tension, we're gonna notice that that wave starts moving a lot faster. Okay, so that means the greater the tension, the faster a wave will move. Conversely, if we go to a low amount of tension, it's really gonna move slowly. Okay. So this is something that really comes into play with guitars and pianos, for instance, how tight those different strings are. Because if we have different speeds, that'll give us different frequencies and pitches of those sounds. So that's where tuning those instruments really come into play in making those strings tighter to make those waves move faster, have a higher frequency, or make those waves move a little bit slower, lower frequency, and thus lower pitch. Okay, so the other factor that will impact how quickly our wave moves, which will then impact our wavelength and frequency, is our force of tension. Another relationship or another equation that will tell us how quickly a standing wave will move on a string. And that is going to be the idea that our velocity of your wave is equal to the square root of your force of tension divided by your linear density. Okay, so given this the force of tension of a string and the linear density, so how that mass in kilograms is distributed amongst its length in meters, will tell you how quickly that wave will be able to move. And since it's a mechanical wave, that velocity is only going to depend on your force of tension and that linear density. Okay. Once you determine your velocity using that information, we then could potentially use the equation from earlier in this unit that our velocity is equal to our wavelength and our frequency. Okay, so the medium determines our velocity, and then our velocity then determines the wavelength and frequency of that wave. Okay. So that is kind of the last little bit of notes to help you with the homework. I am going to go through some examples on the homework packet to help you guys out. So if you'd like to keep watching, you certainly can, but you should have all the information you need here to get started. 44. Okay, so here we're given the string vibrates 45 cycles in 10 seconds, and we want to find the frequency, period, wavelength, and speed of the wave. Okay, so keep in mind here, this is a standing wave. And we are going to see that we have 3 halves or 1.5 wavelengths in the length of the string. Okay, so if you guys remember, if it's 3 halves wavelengths, this is going to end up being our third harmonic. So we are looking at a third harmonic here. Okay, because remember our pattern was whatever harmonic we have over 2 times our wavelength is going to be equal to our length of a given harmonic, of a given string. Okay, so if we look at this one, the string vibrates 45 cycles in 10 seconds. Okay, so given that information, we are going to be able to find our frequency, because we know frequency is how many cycles do we have per second. Okay, so how many cycles do we have in a second? So if we want to get our frequency here, if we have 45 cycles in 10 seconds, we're just going to divide those to see how many cycles we have in 1 second. And we'll find that we have a frequency of 4.5 hertz. Okay. The second thing we wanted to find here was our period. So there's a couple different ways we can find our period. Our period is how many seconds it takes to have 1 cycle. Okay. So here it tells us we have 10 seconds for 45 cycles. So to find how many seconds it is per 1 cycle, we can just divide those, and we end up getting 0.22 seconds. You guys might notice, or you might remember that frequency and period are inversely related. So if you wanted to, you could also find your period by taking 1 over your frequency, which is 4.5, but you'll get the same thing. Okay. So there is our frequency and our period. Those give us information about how long does it take to have 1 cycle. Okay. So then the next thing we wanted to look at was wavelength. So we already noted that we had 1.5. There's 1.5 wavelengths in the length of the string. Okay. So this problem is nice enough to tell us that the length of our string is 6 meters. So we know in that 6 meters, we have 3 halves of our wavelength. Okay, so what we want to do is we want to solve this for wavelength. So we're going to multiply each side by 2/3, or we can think about, because multiplying by the reciprocal is the same thing as dividing by a fraction. And we'll find that our wavelength here ends up being 4 meters. Okay, so you guys can rearrange this equation to solve for your wavelength if you are given your length. Okay, awesome. So now that we know our wavelength and our frequency, now we can go ahead and solve for our velocity. And I'm just going to carry that on down here, because we know velocity is equal to wavelength times our frequency. So if our wavelength is 4 and our frequency is 4.5, we can multiply those together to get a velocity of 18 meters per second. Okay. Awesome. A little aside here, you guys, something that's kind of fun is we know this is our third harmonic because we have 3 halves of a wavelength, and we saw that frequency was 4.5 hertz. If we wanted to get the frequency of that first harmonic, all we would need to do is divide this frequency by 3. Okay, the problem's not asking for it, but if we wanted to, this is what we could do. Because we know whatever frequency of harmonic we're on is equal to whatever number harmonic we're on, or n times that first frequency. So for this wave, our fundamental frequency, or the lowest frequency where we could have a standing wave, would be 1.5 hertz. Okay. Again, we're not looking for that information, okay? That's just some fun extra info. But yeah, just to kind of help you in the future. All right. So then the next one that we're going to take a look at is number 56. Okay, so for number 56, it tells us we have a wave with a frequency of 50 and a wavelength of 1.5. We want to find the tension in the string at the linear density. Remember, that's that mu is 0.8 kilograms per meter. Okay, so we know if we're looking for tension, our equation of the tension in it is that our velocity is equal to our force of tension over our linear density. But before we can solve this, we don't know our velocity or our force of tension, so we would want to solve for our velocity first. So since we're given the frequency and wavelength, we can multiply those together and find that this wave has a velocity of 75 meters per second. Okay. Now that we know how quickly that wave is moving, now we can plug it into our other equation for velocity, that our velocity is equal to our force of tension over your linear density, and solve for your force of tension. Okay. Awesome. So now that we have 2 equations for velocity, we're going to be able to use those in conjunction for one another. But to solve this, we would square both sides. So we'd have 75 squared is equal to your force of tension over 0.8. Remember, get rid of that square root first. And then we'll multiply each side by 0.8. And we would get a force of tension of 4,500 newtons. So it's a very taut string. Awesome. Yeah, so that is it. Let me know what questions you have as you are working. Otherwise, we'll go over them tomorrow. I hope you guys have a great day.